Hello, students. Welcome to another amazing session on coordination chemistry. Now, today we are going to discuss a legend in coordination chemistry, a legend invention by a legend person, and why am I using the word legend, right? So, how is this a legend theory, right? We teachers do have a habit of overemphasizing or giving a lot of credit to certain theories and almost every theory that we teach. But this particular theory, right, in coordination chemistry, I'm using the word legend because this is nothing short of a legend. So why this is called a legend, I'll give you a few reasons. Why this person, Alfred Werner, he got Nobel Prize. Well, you will think there are a lot of people get who got Nobel Prize. Every year in chemistry, there are at least 2 to 3 or 1 to 3 people who get Nobel Prize, right? Well, let's look into this theory and understand how this is important, right? So imagine you are inventing a computer in 1800s, or you're talking about something, very ahead of time. So Werner's theory was almost 1,000 years or 1,500 years ahead of his time, right? So just imagine this guy talked about coordination compound, not just talked about it. He explained the bonding, he explained the structure, he explained the overall constituency, how the coordination compound is formed before even the discovery of electron. Just let that sink in. Before even the discovery of electron. This was done in 1893. So let's see what he did. Okay. So Werner's theory was the first attempt, obviously. Before you see this very old 1893, right? So first attempt to explain the bonding in coordination compounds. Very first attempt. See, in that time, we probably didn't, a lot of people probably didn't even think about bonding, right? We didn't even know about atoms, right? As I said, even the electron has not been discovered yet. Okay. So it was a first attempt. And you see, J.J. Thomson discovered J.J. Thomson discovered electron in 1896. Look at this. 1896 and this came 1893. So even before the discovery of electron. So just imagine the how long-sighted or how revolutionary or how ahead of time Werner's ideas were, right? At least 100 years. Or as I said, this is even now it holds relevance. Or so a lot of the things that Werner discussed has been experimentally proved or observed after let's say 100 years or something. Okay, so let's see. So what he did was won Nobel Prize in 1930. One of the early days of Nobel Prize, but he won the Nobel Prize. And when we go through the Werner's coordination theory, and you relate that with the time period that he discovered this, you'll understand how amazing this was and why this was worthy of Nobel Prize. Okay. So, well, his study spanned over 20 years, and you will understand why it took 20 years or how thorough was Werner through the 20 years, right? So, let's see. So complexes, coordination complexes, they were complete mystery during that time of Werner, or even as I said, even to 100 years if you go, it was complete mystery. We didn't know how they were making the bonds, or how they were, what were their structure, what is it that making them this particular different from double sort or something. Okay, let's take an example. For example, okay, let's say there was a question that eluded scientists. Why does why does okay, why does salt like COCl3, so cobalt chloride, right? COCl3 react with react with a varying number of stable molecule like stable molecules or compounds such as NH3, right? NH3 to give several new compounds. Several new compounds, right? So this was a question that eluded scientists because it doesn't make sense. By that time, probably there was a theory of stoichiometry and everything, but that would mean two things reacting, right? Two things reacting and forming something that should follow a certain stoichiometry. And we could also argue that two elements can form multiple compounds that can have multiple stoichiometry. But here, two compounds, two molecules, they are reacting in multiple proportions and giving several new compounds. How does this happen? That also, two stable molecules or compounds are reacting, right? So let's see what do we mean by that is, right? Whenever we talk about a reaction, it's always good to write a equation, chemical equation that will give you much more idea that represents the whole quantity and qualitative analysis that we can make from that reaction, right? So let's suppose we have COCl3. Okay, I'm not writing the states or anything. This is just to understand. Okay, and 6NH3. Well, COCl3 did react with 6NH3 and it produced. Writing this dot, that means it's a direct compound, or which means that NH3 is there in that crystal. Okay, we will come to this part. You might have seen this in double salts and everything. Next is COCl3 plus 5NH3. So you might think one COCl3 will react with only 6NH3. No, it also reacted with 5NH3. Right? Then it also reacted with 4NH3. So we couldn't explain first of all, what is forcing COCl3 to react with NH3, right? Both which are supposed to be stable compounds on their own. And if at all it reacts, suppose it just crystals and rearranging somewhere, why is there a range of values? Why can 6NH3 react at the same time 5 and 4 also can react? If 4 was enough, why there are 5 NH3 molecules reacting, 6 NH3 molecules reacting, right? So people could not explain this, right? Why this happens. And also, what are their structures, right? So what are their structures? A very important question, right? So these two questions, right? These two questions, it eluded scientists, what made people confused. What is happening? Why is this happening? How is this happening? Right. Now that's what Werner tried to solve through his coordination theory. So let's see. You need to understand, now we are able to look at the structures of any compound using X-ray diffraction technology and everything. But back then we didn't even know about the diffraction or X-ray or anything, right? So Werner had to go through reaction chemistry, right? So what he did was, Werner, this is where it becomes very, impressive. Werner did not have any technological advancements such as such as X-ray diffraction, etc. Right? So many things we can, to understand the mass and everything, or formula we can use mass spectrometer, etc. But X-ray diffraction, I'm using that word because it helps you understand the molecular structure. Okay, but he used reaction chemistry, used reaction chemistry to explain all these. So amazing. I mean, when you think about it, so amazing. It will force you to, be more creative, because when we don't have anything, necessity is the mother of creation, right? So Werner did not have any technological advances. So what did he do? He made use of what was the available data to him and made amazing, brilliant deductions from it. Right? It's not about whether we have the best facilities or anything. It's about how we use it, right? How smartly we use it. That's what Werner did, and that's why I said this is a stuff of legend. Now let's try to do so. He was able to explain what were he able to explain. One, nature of bonding. Two, so nature of bonding, structure, right? Yeah. So these three things, sorry, these two things, nature of bonding and structure, very important if you think about it, because well, we didn't know about most of the other properties such as magnetic, etc. That didn't come into the play because you need to understand this happened in 1893. Anyway, so how did he do this? How did he understand the nature of bonding? Right? So using reaction chemistry, Werner not discovered, Werner concluded, let's say. Werner concluded coordination compounds coordination compounds show two different valencies. Two different valencies. And what are they? I'll just list it out here and we'll explain it in the next slide. First one is primary. Well, it makes sense, right? Primary, the first one, primary. Second one, secondary, right? Primary and secondary. The bracket you can write. Okay. So I'll explain what is primary valency and secondary valency. And this is a important topic. Why is it an important topic? It's an important topic because questions do come from this topic, right? We check the previous year questions of NEET or JEE mains or even let's say in CBSE, you do get questions in this area to find the primary and secondary valency. So we'll go through it. We'll discuss some questions in the end as well. No worries, right? So now let's go to the next page. So I hope you understood the first conclusion that Werner came into the primary and secondary valency. Now let's see what is primary valency. Okay. Primary valency. Okay. So he said these give rise to first order compound, which means COCl3. See the COCl3 from, let's say, COCl3 6NH3. Take an example. It could be 5NH3, 4NH3, whatever. So COCl3 from this. Okay, this gives to the rise to the first order compound. Okay, and this correspond to the valency. Very important point here. Okay, correspond to the valency, now known as, obviously you learned this what I'm going to discuss. So now known as oxidation state. You know how to calculate oxidation state. So you calculate oxidation state, you get primary valency. Easy, right? So correspond to the valency, now known as oxidation state. Okay. Or in modern terms, I'll give a definition. It is number of primary valency corresponds to the number of charges on the central metal atom. Clear? So number of primary valency corresponds to number of charges on the central metal atom, and you know it is metal. It cannot be negative. Could be zero or negative. We will come into that. It mean in almost all the cases it will be positive. Okay, because it is metal, it wants to give away electron. Okay, that is the definition of the metal. Electropositive, wants to give away electron. Okay. So we'll take an example. I'll go to next page and we'll take an example. Example in the sense we discussed that example. So let's suppose in the coordination complex introduction, we talked how we can write a complex and everything. Suppose I'm writing CO and I have a NH3 6 Cl3. Now we check this. What will be the charge on CO? NH3 is 0, right? Right. NH3 is 0. Cl is -1 because it is. So it is Cl minus, right? So CO will be +3, which implies primary valency is +3 or 3. You can write 3, no problem, right? So I'm not going to detailedly go with the calculation of oxidation state. That's what we did for the half of the redox reaction chapter. But anyway, all of you revise a bit into how to calculate the oxidation state. It's very simple anyway, because the whole thing is neutral. So 0 is equal to minus 3 plus x. So x will be plus 3. Okay, cool. So here primary valency is 3. We'll take another example just so that you can understand. Suppose I'm taking an example, CO H2O 4 Cl2 Cl. So look at here, okay, Cl2 Cl. So we have 3 chlorines, so 3 Cl minus, right? So 0 is equal to x minus 3, which implies x is equal to 3 plus 3, 3. So that is the primary valency. X is the oxidation state of cobalt. H2O is neutral molecule, so zero charge. Anyway, I hope the primary valency part is clear to everyone. Now let's go into what is secondary valency. Also, you can, after explain secondary valency, I'll give some tricks or some fast methods to understand between primary and secondary valency. No issue. Secondary valency. Okay, secondary valency. These give rise to higher order compounds. Higher order compounds. Okay, higher order compounds. Okay, so if I take an example, for example, you have CO Cl3 dot NH3, NNH3, that meaning could be any number, 6, 5, 4, etc. It could be 3 also. We'll discuss why it could be 3, right? From COCl3 and NH3. Okay, clear? So COCl3 NH3, right? COCl3 NH3, see that the primary let's say lower order, first order compound was only COCl3, but higher order compound is COCl3 NNH3. Clear? Now let's see, how do we define this, right? And these are directional. These are directional. Well, the primary valency is non-directional because, as you said, it's oxidation state. So it's just like ionic compound. Okay. So it doesn't have any direction. These are directional, very important, because this is what that will help you with the structure. These are directional. Modern terms, if we define this, you can get it as number of secondary valencies equals the number of ligand atoms coordinated to the metal. Very important point. So primary valency, ionic bonding. Secondary valency, coordinate bonding. So this is what that makes a compound coordination complex, right? So this is also called coordination number. So number of ligands, that is, or number of coordination bonds that is made towards the central metal atom, that is called coordination compound, sorry, coordination number. It's also called secondary valence. Okay, so we'll take example. Okay, now let's see. You learned about ligands, right? So in general, we'll talk in general. So ligands, or we'll continue a bit with the secondary valency, then we'll go into the comparison, then as I said, the trick, and then we go to some questions. So comparison, ligands are generally negative or neutral ions or molecules, right? I hope you, in the introduction part of the thing, we have learned about what are ligands, the types of ligands, and etc. Names of ligands. Even you haven't, no problem. So an example, this is Cl minus. Example, this is NH3. Generally, they are positive and negative, but could also be positive ions. What is an example for positive ion? That is no plus. Very important. There are only few positive ions. So in the part of ligands, we already learned, you already know about this, called nitrosonium ion. But if you haven't, you will learn about this in ligands. No issue. NO plus. Okay. So now each metal has a characteristic number of secondary valency. Because you know now that each metal, how does a coordination bonding take place? A pair of electron is being donated, right? So there is a number of limitations for how many electrons can be, how many vacant orbitals does a metal have. The reason metal take place in this coordination complex formation is because of the vacant d orbitals, right? Or s or p, whatever, vacant orbitals, right? So there is a limit to how many electron pairs a metal can, accept. So there is a each metal has a characteristic number of secondary valence. Okay, so that will be very important for us to determine how the complex is going to look, or how the complex is going to take part in a reaction. Okay, cool. So let's see. If you look at this, and I'll give, so the discussion about secondary valence is over. I'll explain some comparisons, right? So you see, primary valency is satisfied only by negative ions. Why is that? It's because primary valency is like ionic bonding. Okay, so keep this in mind. Primary valency is like ionic bonding, or it's actually ionic bonding, right? There is a metal ion and there are negative ions that electrostatically attracted to each other. We think secondary valency can be satisfied by negative, neutral, or positive ions. Why is that? Why is that? Because secondary valency is number of coordination, and it can be done by negative, neutral, or positive, because it's like, it's not like it actually is, but this is just a trick to keep in your mind, like coordination bonding. Cool. So primary valency, think of it as ionic bonding. Secondary valency, think of it as coordination bond. So primary valency can only be satisfied by negative ions, but secondary valency can be satisfied by negative, neutral, or positive ions. Okay, cool. So see, these comparisons may lose some edge over very advanced examples and stuff, but we are discussing about Werner's theory, so this will hold true for every question that you're going to come across. Now let's see an example, right? So let's suppose okay, CO in COCl3, let's say NNH3, okay, NNH3 has three primary valency and six secondary valency, right? Okay, so if this is the case, and I'm going to give different compounds and we are going to explain how they are formed, okay, how they can be, because this is something an atom has to, this is important, this is something the complex has to comply by. Okay, so let's try to explain different complexes, this different complexes of COCl3 and H3. So the first one, COCl3 6NH3, right? So you see, or we can write it in a different way, but we'll understand that. So COCl3 6NH3. So who can only satisfy? So what is primary valency? The 3. Who need to satisfy this? 3Cl minus. Correct? And secondary valency is 6. Who satisfy this? Who can satisfy this? Ammonia. Sorry, ammonia, right? So 6NH3. So what will be the structure of this? Or what will be the formula of this structure? We will come into later. Will it be like this? No. What will happen is, because the thing ligands inside the coordination sphere will have to make coordination bonds, and only NH3 is making that. So 3Cl is outside. Clear? So now you understood this. Clear? And also, I'll go into the experiment of AgNO3 later on, right? How did he come into this, right? So we'll go into that just after explaining the other two compounds. Just to, prove that this was correct, we'll go through that. COCl3, let's say 5NH3. Now what can we do here? 5NH3, right? So primary valency, well, it remains 3. Secondary valency, because that will not change, that has to be satisfied by whatever we have in the complex. Primary valency, who can satisfy it? 3Cl minus, right? They can satisfy it. Secondary valency, we need 6. We need either neutral or negative or positive 6 ligands. We need 6 coordination bonds. So each NH3 has here NH3 has a lone pair, so it can do one coordination, right? And we have chlorine as well. Okay, so 5NH3 plus 1 Cl minus, which meaning 1 Cl minus here is satisfying both primary valency and secondary valency. Very important part. So we can write, so that means 1 Cl will be inside the coordination complex. So CO NH3 5 Cl Cl2. Okay. Once we go for that AgNO3 experiment, you will understand why this is very important. Okay. So next is CO Cl3 4NH3.
Okay, we know what is primary valency. 3, it's given. Secondary valency 6. So this is satisfied by obviously 3Cl minus. Now this, who satisfies this? Obviously 4NH3 can only satisfy secondary valency, but there are two more valencies that needs to be filled. So who will do that? 2Cl minus, which meaning two Cl minus ions in this case will satisfy both primary and secondary valency. Okay, cool. So when we look at that, so what will be, so that means these two Cl minus has to be inside the complex because it is satisfying secondary valency. CO NH3 4 Cl. Okay, cool. Now what we will do is we'll do a question. We'll do a question from maybe, let's say, let me go to the next page. Okay. So let's discuss a concept. We'll do the question in the end. We'll do an so we'll discuss the concept or particular concept at the topic, and we'll do the question on that. Okay. So let's see. If I take, okay, MCl plus AgNO, what will happen? To create AgCl plus MnO3, suppose, right? Almost every metal is capable of doing that. But AgCl will actually precipitate. This will be this, this will be this, this will be this, right? So if you have n, right, then we need to take n number, then we will get NaGCl. Clear? And we will have. So this experiment using AgNO3 and looking at the precipitation, how many moles of AgCl is precipitated, we can identify how many moles of Cl is there or how many moles of Cl minus will produce. Because in this case, we will get Mn plus aqueous because it's a salt plus NCl minus. Correct? That's why this Ag plus reacts with this and create AgCl. But this will only happen, I mean, this will only happen if we have Cl minus in the solution, right? So you see CO NH3, let's say 5Cl, right? How will this dissociate in water? Okay, you know the components inside the coordination complex will not undergo ionization. Otherwise, what is the difference between coordination compound and a double salt, right? So you will get CO NH3 5 Cn plus. So this will be 2 plus. Why? Because we have 2Cl minus. So 2 negative are going, so it will become positive. So now if you add AgNO3, right? Let's say excess. I'm adding excess because how much ever it is, I want AgNO3. I don't want AgNO3 to be the limiting agent. Now what we will get is we get 2 AgCl. Why? Because there are 2 Cl minus. So this and you need to understand Cl outside the coordination complex, it's not responsible for secondary valency. So this particular experiment, let us understand how many of the Cl are involved in primary valency or both secondary and primary valency. Is that clear? So we'll do a question. Okay. So let's see. Question. This is from NEET 2017. My memory serves me right. For for a compound having general formula. Okay, I'll just write the formula, not in the coordination form. CO, Cl3, N, NH3, right? Has four different forms, right? That just means N could be four different values, four different forms. A comma, B comma, C comma, D, right? Upon reacting with AgNO3, upon reacting with AgNO3, A comma B comma C comma D creates how many? Let's see, 3 comma 2 comma 1 comma 0 moles of AgCl respectively. Okay, that is a data. Find out. Well, I'm twisting the question to be a subjective question so that you get an idea. You don't go out just guessing the answer. Find out A comma B comma C comma D. So you just need to write. You need to find out what are the n values for A comma B comma C comma D. Okay. So let's solve this question. So what are the important points here? I'll highlight those. General formula, right? Four different forms. So N is four different. Then ABCD on reacting with AgNO3 creates 3 comma 2 comma 1 comma 0 of AgCl. These are the important points. Now let's see what to do, how to do this question. Okay. So to find out A, okay, what is the data? Creates 3 AgCl, which implies 3 Cl are outside, or they are called counter ions. I'm just using very simple terms, outside, which implies what does it imply? All the chlorine are outside, right? If all the chlorine are outside, who is satisfying the primary secondary valency? Secondary valency. What is secondary valency? 6, right? Who is going to satisfy this? Only satisfied by NH3. How do we know only NH3? Because all the chlorine are outside. We only have 3 chlorine and they are outside. They cannot satisfy the secondary valency if they are outside. Right? Only satisfied, which implies 6NH3. Sorry, 6NH3. Which implies what is the formula? E is equal to, or E is corresponding to CO NH3 6 Cl3. Okay. So from here, we understood 3Cl has to be outside because whatever chlorine inside that will not ionize. So that will not react with AgNO3. Correct? So 3Cl has to be outside. 3Cl, or I'll just write Cl minus, right? Cl minus has to be outside, which meaning they cannot satisfy secondary valency. So it can only be satisfied by NH3. So NH3 has to be 6. Okay? This is clear? So N here is 6. So you can also write CO, Cl3, 6NH3. That is A. So what about B? Check what is B. B, what is the data? 2 AgCl is created. Right. See, during the exam, you will not have to do this long process. Now I'm doing it so that you get an understanding and you can do the questions faster during the exam. But you try to understand it every time when you learn a concept. First few questions you do it detail and understand the concept. Make it that neural network pathway in your brain, make it very permanent, make it very clear without any misconceptions or confusions. So 2 AGCL is created, which implies 2Cl minus are outside complex. Okay, which implies there is one Cl minus left, right? So secondary valency is satisfied by 1 Cl minus and NH3 molecules, which implies 5 NH3 because secondary valence is 6. So you get COCl3 5 NH3. Clear? So this is how CaCl3 5 NH3 is possible. And next thing you can already do, right? Because it's 1, so 1 has to be outside, 2 has to be inside. I'm not going to explain this. You can do it yourself. So you'll get 2 CLR, 1 CL is outside, 2 CL is inside. So 4 NH3, so 1 CL minus outside, 2 CL minus 4 secondary valency, which implies how many NH3 is needed? Only 4. So CO so you can write COCl3 dot 4 NH3, that is C. Correct? Now you see D, no AgCl, which implies no Cl minus outside. So secondary valency 3Cl minus plus NH3, right? Which implies 3 NH3, 6 minus 3, 3. So COCl3 dot 3 NH3. Or you can draw the structure as, formula as CO NH3 thrice Cl thrice. Okay, so no formation of ion when dissolved in water. So this was a question from NEET 2017. I hope you understood all of this. Now that we discussed primary valency, secondary valency, and discussed the question and all the depths and everything, we are going into how Werner, how Werner predicted the structure and how close he came, right? So let's see. Secondary valency, so structure. How did you know that? Okay. There won't be a lot of questions on structure. It's just about how we came into that structure and how close he was to the structure. So what he did was, let's say, according to secondary valencies, he proposed various possible structures, possible arrangements. Why only according to secondary valency? Because primary valency is non-directional. Secondary valency is only directional. So that is only going to affect the arrangement. So for an example, arrangements and predicted number of isomers and later cross-checked it with with experimental data. So orally, I'll explain this again. So what he did was, according to secondary valency, he proposed various arrangements, right? So, and those arrangements here, with that arrangement and arranging in different positions, he tried to predict, or he found out how many isomers are possible, right? Mainly, geometrical isomers are in that point, right? He tried to predict that, and he kept that number, right, for different arrangements, and he cross-checked with experimental data. He experimentally found out how many different isomers are possible, and he checked that. And cross-referencing that, he was able to identify which arrangement is the correct structure. Okay, so let's take an example. For example, or I'll go to next page, that will be better. For example, secondary valency equal to 6. So we have a central metal atom, and around it we have 6 ligands, right? So what are the possible arrangements? What are the possible arrangements, right? So possible arrangements, let's see. You can have, let's say, central metal atom, and you can have it as, you know, planar hexagon, right? So planar hexagon, which meaning, suppose this metal is in the center, and all these positions are ligands. Okay, so like that. Well, this is one possibility. It can exist like this, right? Stable, or whether this is a thing that he didn't know about because this was in 1890. So BSEPR and all these things hasn't come into play. This is one possibility. Second possibility is because he was just thinking with the geometry, nothing else. He didn't know about BSEPR, hybridization, etc. Trigonal prism, which meaning we have a triangle base. Okay, have a triangle base, and we have a triangle stem. Yeah, pardon my drawing. Okay, so metal could be in the center, and ligands could be in all these positions, right? 6 ligands here also. Clear? Now, what is another possibility? Octahedron. Okay, octahedron. Octahedron, you know, like a metal here. Well, it's easier for us now because we know about. Okay, try to draw this. Let's visualize it in 3D. So see, see. So this is octahedron, right? So the ligands could be in these positions. Now, if you look at this, right? So what he did was he tried to let's suppose if you have MX6, okay. So what he did was, let's go to the next page. He calculated, each uh, possible number of isomers for each kind. Let's say, I'll make a small table. I'm not going to discuss everything in detail because that will just be and not that will not be necessary, and that will not aid to our preparation. So complex, let's say there's a type of complex and mixes. Okay. Then let's say observed isomers, right? Then we have the predicted from, let's say, octahedral planar hexagon, right? And trigonal prism. So you see, observed how many isomers are possible, right? So we observed it was 1, and for mx5y, that means there are two types of ligands, right? So we observed, then again only one, right? These are experimental, right? You need to understand it. He was really little skeptical or little doubtful about this discovery. Why? Because during the time of observing or identifying how many isomers are there, there could be a lot of errors. So here he found two. Later on, we will learn about how we can find out this. We will learn the isomerism, right? So if it was octahedral, MXS is 1. I'll discuss octahedral, how we came to this number. Otherwise, we'll discuss this. So let's see, octahedral, right? If we have octahedral, I'll draw different octahedral. Look at this. X, 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 X. Is there any other possibility? No. So just one isomer. What about MX5Y, right? So that also, if you check, what does this mean? This means wherever you put Y, the all are equal in positions, right? You put here, 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 anywhere. So only one. Now what about MX4Y? So now there are two possibilities. If I put Y here, I can put the Y in two different positions. Understand? I can either put it here, which is 90° to it, or 180° to it. If I put it here, right, this is one. Now I can have one more isomer of this type, M Y here. If I put Y here, X, 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 X. So these are the two different types of isomers possible for. You need to understand this is geometrical isomers. These are the two types of isomers, possible for MX for Y2. Okay, clear? So this is cis and this is trans. We will come into that in isomerism. No issue. So we have two. Now, if you go into the next type, MX3Y3, right? So here also we only have so suppose I put all the X in same plane. Okay. So I have Y here, Y here, Y here. Then I put all the Y in the same plane. X here, X here, X. To try to do it, is there any other way of putting any other possible arrangement? No, these are the only thing. And yeah, this is called mer and this is called fac. We'll come into this later, but just a heads up, right? So only two. Okay. So let's fill up the table. So octahedral, we had 1, 1, 2. Planar hexagon, we had 1, 1, 3, 3. You can try this, but it's not needed. So you don't have to try it. Just learn it as a, okay, this is what it was. 1, 1, 3, 3. So from here, he identified it is up when when the secondary valence is 6. If sorry, if secondary valency is 6, which implies arrangement is octahedral. See how without any technological advancements or anything, how he was able to use his splits and conceptual understanding and logic to find out the structure. And this came out to be true, right? This came out to be true. This could be explained by CFT and all these experimental technological things later on, but this came out to be true. Okay. Then we can discuss about the 4 as well, but just this is the idea. You just keep this in mind, right? We don't need to. I mean, this is the same is in the same way. Okay, I'll discuss that as well. Right? We'll leave no stone unturned. Let's see. 4 secondary valency equal to 4. What are the possibilities? Possibilities. One is square planar, right? One is tetrahedral. So okay. And depending upon the number of isomers and everything, he found out it was tetrahedral most of the time. But you need to understand Werner's theory isn't perfect. It happened in 1893. So for the complexes that he had at that time, it worked, right? But later on, we found out so many other. We synthesized a lot of complexes. Then we checked it with a lot of other different, you know, different technologies and stuff. So we found out that it's not always tetrahedral, could be square planar as well. So this particular observation wasn't very perfect, but he found out why because in mx2y2 tetrahedral there is only one isomer. Whatever the thing is, there is only one isomer. All the positions are same. But square planar it could be different. Right? Square planar will give isomer, this will give 1. So that's how we found it. It was tetrahedral or square planar for that matter. But the same way that we did, the secondary valency 6. So this is how Werner revolutionized, or Werner did some amazing, got some amazing understanding about coordination complex and laid the foundation for every other advancements or theories that we have in coordination complex. So we discussed a very possible question from NEET 2017. You guys practice a lot of other questions and just try to understand how a scientist or that time scientist doesn't have the tools and everything that we have right now. How a scientist, a brilliant mind, our brilliant mind, even in 1850s or 18, because his work spanned 20 years, 1870s, used his very limited knowledge of chemistry, very limited advancements in science and technology to explain and make sense and make a theory of something that seems so confusing, right? So you guys always wonder why do we learn about the history? Why first theory, second theory? Because we have the more latest theory. But we are learning about these because we are trying to understand how did they come into that? What was the thought process of the origin or inception of all these wonderful concepts, right? So I hope the this session about Werner's theory has been informative and helpful and also very motivational to you. So we'll see in the next class with another amazing theories and history of chemistry and some amazing questions that you can expect in NEET or JEE Mains or even your central university exams and etc. Goodbye.